Hi, my name's Jim, and I'd like to talk about Schrodinger's cat. I'd like to talk about Schrodinger's cat for PhysicsFM. PhysicsFM is a podcast featuring my friend Randy and me, where we talk about various physics concepts. Right now, what we're doing is we're talking about Quantum Paradoxes by Akira Aronoff and Daniel Rohrlich. It's a very interesting book that uses the concept of a physical paradox, both to explain quantum mechanics and to argue for a particular interpretation of quantum mechanics. And Schrodinger's cat has a very special place in this book. It ends up right in the middle in Chapter 9. Because Schrodinger's cat is going to tell us why we need an interpretation of quantum mechanics. So I'd like to go through Schrodinger's cat, go through this paradox here in a way where I can illustrate it, because in the podcast, obviously, it's just Randy and I talking, so it's hard to see what's exactly going on. So I'd like to go through and explain it in this video format where you can actually see some illustrations and hopefully get a better idea about what's going on in the paradox. All right. Everything that I'm going to say about quantum mechanics and from Schrodinger's cat is just as valid for any quantum mechanical measuring system, all right? That's what we're going to look at, is a quantum mechanical measurement system. And so we need to understand something about quantum measurements first, and I'm going to explain that using the Geiger counter. You know, what does it mean to be a quantum measurement and so forth. And then I'm going to go on and I'm going to talk about Schrodinger's cat. I'm going to set up the paradox, and then I'm going to explain the implications of the paradox at the end. I'm not going to go through and talk about any interpretations, okay? The interpretations, we talked about that extensively at www.physicsfm.com. You can listen to the podcast. It'll be perfectly fine. The podcast is on iTunes as well. You'll have a great time listening to it. Go ahead and do that. But this will set some of that up. Now, we do talk about the paradox in the podcast, but again, we have illustrations here, and I'm not in the middle of a conversation, which means I can go through and explain it the way I think is most logical. Okay, so I'm going to go through and talk about all of these topics, right? And we're starting with this Geiger counter, right? And the Geiger counter, basically the active part of the Geiger counter is going to be this Geiger-Müller tube, right? And that's going to be connected to, say, a speaker. That's what you normally think of when you think of a Geiger counter, is the speaker clicking every time a radioactive particle is detected, right? The sort of sound that you remember from all sorts of movies and maybe even from a science class or two. So I want to just go through and show that this is a quantum measurement. So I'm not going to explain quantum measurements so much. I want to do another video just for that. But here I want to just show that it's a quantum measurement and sort of set you up for what's going on later on. All right. So how does this Geiger counter work, right? The Geiger counter works when an emitted particle, which is either an alpha particle, which is really just a helium nucleus, or a beta particle, which is an electron, enters into a gas-filled tube. And that gas-filled tube has a really high voltage applied to it. There's a center anode, which is just a wire, and that gets charged up. And the outer cathode, which is just a cylindrical shell around it. So you have a radial electric field going all the way down this cylinder. And the emitted particle gets in there through this window, and when it goes in, it's going to collide with something in the gas, right? And so it's going to have a quantum scattering event with that one particle. When it hits that atom, it's going to ionize the atom, all right? And the ion will go towards the cathode because it's positively charged. It'll go towards the cathode, which is negatively charged. And it'll do that relatively slowly because it's a really heavy thing compared to all of the other things in the system. And then the electron that's liberated from the atom when it's ionized, that'll go off and do its thing, right? It'll go off into the gas some other direction. It'll try to go towards the anode, towards the center of the tube. All right, and the emitted particle, well, that just keeps on going. All right, so that's very important. The emitted particle just keeps on going. It doesn't get reabsorbed or anything like that. So now you have this electron in there. It's going really fast, and it's a charged particle in the tube. It's acting exactly like the emitted particle. In fact, the emitted particle could be, like I said, a beta particle. It could be a really, really fast electron that was emitted from the radioactive source. So it, too, can cause more scattering events, right? So it hits an atom, it ionizes the atom, and now you have two free electrons running around with another ion going towards the cathode, but the ions, because they're not really important, I'm not going to illustrate any more ions because, you know, this picture is going to get complicated enough already without illustrating the ions. You're just going to imagine a bunch of red lines going towards that cathode if you'd like to. Now, each of those, again, they can collide with more gas atoms, and they can keep on doing that over and over and over and over again. So this one emitted particle with its first ionizing event, that can end up giving you 1 million up to about 100 million particles, electrons that are going to crash into this anode, right? But the emitted particle doesn't just collide once. Just like this electron can collide multiple times, so can the emitted particle, and that'll happen over and over and over again. So you'll end up with a billion, 10 billion, somewhere around there, that number of particles hitting the anode. That's going to depend on how much voltage you put on and all sorts of other things, the pressure of the gas and so forth and so on. So all of these things, this Townsend discharge, this Townsend avalanche, you get a whole bunch of these electrons coming down, hitting that anode, and it creates a voltage pulse that goes out. And that's what goes to your speaker or to your electronic counter if you want to use a counter instead. But it goes to your speaker, makes a little bit of a noise, and that's your entire measurement. So that's going to happen every time a particle goes into your window, right? Every time a particle goes into your tube. That obviously is going to take a lot of time because there are a lot of little things that are happening. So this measurement does happen in a finite amount of time. The emitted particle has to go through in some time, and the avalanches stop after a while. And in fact, they all stop at about the same time and end up with a pulse. And that's why you end up with little clicks, right? It takes a finite amount of time because the measurement stops. Otherwise, you'd end up with the sort of wavy sounding noise from the speaker. Instead, you just get clicks, right? So it takes a finite amount of time. All right, so that's the first thing that we need for a quantum measurement. The next thing that we need for a quantum measurement is going to be that it doesn't, or is that the thing that you measure, in this case the click, is going to correspond to the thing that you want to measure. The thing you want to know, the thing you want to observe, which is, has a particle been emitted from the radioactive source? And the answer is here, yes, right? So that's pretty obvious. The third thing is, when you measure this, you don't change the observed quantity. Basically, does the emitted particle stop having been emitted after you measure this? And the answer is no. So what we're saying here is that the emitted particle has been emitted, it stays emitted, and it doesn't get reabsorbed, and we're perfectly fine. This is a quantum measurement. The fourth one, this is probably the iffiest one, that the measurement can be made arbitrarily short. Arbitrarily short is just me saying that it can become short enough that you don't have to worry about changing what it is you're observing, right? Having two particles in the window. And that's pretty much true. You don't get a bunch of these particles in the window most of the time, unless you had some sort of really radioactive source, I guess. You could. I don't know about that. You can talk to somebody who's an expert, and they'll tell you all sorts of stuff about that. But the measurement should be able to be made arbitrarily short, and so you can pick up single emitted particles. All right. And finally, the measurement is a quantum process. And this is very important. And we already said it's a quantum process, right? This is a quantum scattering event. And this is actually something that Aharonov and Rohrlich talk about very early on, is they spend a paragraph or two talking about just when, say, this emitted particle hits one gas atom, right? So when that happens, you end up with a system that's still a quantum system. Right? You still have probabilities. Everything that has to do with quantum mechanics is still there. It's an entangled system, and which means that what happens with the particle has something to do with the atom, but all the probabilities and things like that are still left in there. And you can't say that after this one single quantum event, you now have a classical system. No, you just have a larger quantum system. All right, and so that's where the analysis is going to start when we get to the analysis. So that's about it for the Geiger counter. We've seen that it's a quantum measurement process, and we've seen basically how it works, which is with a whole lot of little quantum scattering events. Fair enough. Let's see how the Schrodinger's cat paradox works. Schrodinger's cat is basically a Rube Goldberg device. All right. Schrodinger invented this Rube Goldberg device, which is, this sort of thing that you remember from cartoons, right? Where you have a mouse in front of some cheese, and there's like a string tied to the mouse's tail, and so the mouse tries to get the cheese, and it pulls the string, and that opens up that string pulls a latch after it's gone over a couple of levers, and that drops the ironing board, and the ironing board hits the dog on the head, and the dog jumps up on the counter or something, and knocks a juice can over, and the juice goes into the cup, and then the guy gets his juice in a nice cup or something like that. So Rube Goldberg device is one of these really complicated devices like that, and it's something that Rube Goldberg invented this kind of cartoon in engineering class. All right, so before he became a cartoonist, before he became a really, really well-paid cartoonist, Rube Goldberg had been in engineering school, and when he was listening to some engineering professor, possibly a physics professor, come in and talk about some, actually I think it was a physics professor, talk about some particular experiment, I think measuring gravity. So the physics professor came in with a really complicated device for measuring gravity, and Rube Goldberg was so impressed by this complicated mass of stuff that he had no idea about what was going on. He invented a kind of cartoon based on it, where he'd have a bunch of different things labeled A through F of the kind I already said, with the mouse and the cheese and the orange juice. All right, so that's what I sort of think of when I think of Schrodinger's cat, as this complicated mess. Now, it only has 4 parts, right? And the first part is the radiation source, right? And the radiation source, it can either emit a particle or not emit a particle with some probability. We understand that more or less about radiation by now. And that's sort of just the first part of this detector, right? The next part is what you're going to actually couple to that radioactive source, and that's going to be our Geiger counter, right? The Geiger-Müller tube. And, that's the whole reason why I went through the whole Geiger counter thing, is to put that in there. Now, that Geiger counter is going to send out a voltage pulse, and that voltage pulse is going to be connected to something that contains some vial or something that contains a bunch of poison gas. Right. And that poison gas is going to be just sitting there waiting for whatever's keeping it from opening, whatever's keeping the vial from opening. It's just going to sit there and wait for that to happen, right? And the final bit of this is the cat, right? And the cat goes into our box, right? And we close the box, and that's going to be our measurement. Our measurement is going to be opening up this box, right? And, in one case, we have a live cat, right? If the radioactive source, like it hasn't yet, does not emit a particle, then we're going to have a live cat. What happens if it does emit a particle? Well, you can probably guess. It emits a particle, and it has some sort of probability to do that, and it has some sort of probability to not do that. And if it does emit a particle, then it's going to couple to the detector, right? So it's either going to be detected or not detected, right? And it's only going to be detected if it's emitted. So, we have this sort of entangled state already, that the detector is entangled with the radioactive source now. And now, after that happens, the poison gas will, its vial will open, and it'll either be released or not released. So again, that gets coupled in with the rest of this. So we still have this probabilistic system. And then, the gas goes in there and it kills the cat. So the cat's going to be alive or dead. So this is the other case, is the cat will be dead. And there's some probability for that, which is exactly equal to the probability of the source releasing a radioactive particle. That is Schrodinger's cat. So the final step is looking in the box and seeing if the cat is alive or dead. If it's alive, you know that the source hasn't released a radioactive particle, and if it's dead, you know that it has. Again, it's a very Rube Goldberg-esque sort of thing for you, right? So now what our question is going to be is, you know, what does this mean? How can we interpret this, right? Because before you look, what a lot of people will say is that the cat is neither alive or dead, because you have this state that goes all the way back to that radioactive source, right, which follows quantum mechanical rules, right? And because it follows these quantum mechanical rules, that radioactive source does not have to have been emitted, right? There's some probability for that to happen, and even if it goes through a peak of that probability and comes back down, it could even go to a place where it goes to 1 and goes back down to 0 again, depending on conditions. It doesn't need to have happened, all right? All that really matters is what happens when you make the measurement. What's happening before and in between doesn't really matter, right, in a quantum measurement, right? It's only when you actually make the measurement, and there are ways to talk about this, and I think I'm going to make a video about the Stern-Gerlach experiment, another Stern-Gerlach experiment that shows what happens when all of these probabilities combine back again, right? And that's a very important issue, is that the probabilities can combine back and you end up with a superposition of states again. So this looks like mathematically like there's a chance that this cat is neither alive nor dead until you actually open up that box. Now, it's a paradox because you have an idea about what's going to happen. You open up the box, that cat is going to be alive or dead, right? Because that poison gas is going to have been released or not released, right? Those are just things that have to have happened, right? So that's the reason why there's a paradox, again, is that you have these two different ideas and they conflict with each other. So let's try to just walk through this and see where we get this coupling to the real world. The radioactive source, we've already said that can't be the case, right? That it cannot be the case that the radioactive source is going to be this coupling to the real world, because it's the source of the quantum mechanical part, right? It's completely random, and it's until somebody actually observes this decay, we don't really know that it's happened. We can act like it's a wave function. It has the strange quantum probability stuff that's a little bit different from regular probability stuff. You go on and you get to the tube. Now, we've already talked about that in another context, right, where we've said that at least as far as that first quantum scattering event is concerned, we're still stuck in a quantum state, right? And there's no reason after that second or fourth or 10 billionth that we've left that case. We've just added more and more stuff into this wave function, right? Now, there are going to be people who talk about, say, a statistical interpretation or a decoherence idea here, but still we're here, and we haven't seen any place where we have to necessarily go from one idea to the other, from quantum mechanics to classical physics, even though we're pretty sure that this detector is going to put out a voltage pulse. So we're still stuck by the time we get to the vial, right, which is definitely a classical thing. Even though this is definitely a classical thing, it's still stuck in this quantum superposition, and it's still stuck in this entangled state. Even worse, so is the cat, right? And the cat should probably have just as much a say in whether or not it's alive or dead as you do, right? It should be able to observe that it's dead well before you observe that it's dead. But as far as quantum mechanics is concerned, he's been stuffed into this wave function. In fact, sometimes there are some interpretations of quantum mechanics where when you open this box, you're part of that wave function, and you don't even really know if this cat is alive or dead. Again, listen to the podcast, and you can hear all about those. I'm not going to get really into that at this point. So we have we have this issue here, is we need to have some way to understand, you know, when the cat switches from being alive or dead, when this wave function decides to go from having these two different possibilities to having just one possibility, when we go from a quantum mechanical state to a classical state, and we don't have a good way to do that. Lots of people have interpretations. An interpretation means basically that it's something that you can't do an experiment on. It's a little disconcerting. Now, I mean, you know, I know this sounds like a Sorites paradox, right? This sounds like, you know, how many little hairs do you have to pull out of your brother's head before your brother becomes bald? Now that's not quite the same thing, because that's a logic paradox, right? Whereas this is a physical paradox, right? There has to be somewhere some experiment to determine where you've gone from one system to another, right? Or at least some experiment or set of experiments where you can sort of define a curve where you have some proportion of quantum mechanics and some proportion of classical mechanics, or some description of an intermediate regime. And again, there are places where people try to do that with decoherence and things like that. How well that works is, you know, something, you know, you can think about, but I'm not going to talk about that here. I'll probably try to talk about decoherence somewhere else as well. But in the end, you know, this is, in a way, very similar, right, to that Sorites paradox. Just instead of a linguistic problem, a vagueness problem, you have a real physical issue that has yet to be resolved. Nobody's resolved this issue, and so we need these interpretations. So, and you're free to choose any interpretation you want, and that's the whole reason why it's an interpretation. In fact, you know, if you listen to the podcast, we go through all these interpretations, and we say, well, none of these work, right? And that's really the case with the interpretations, is none of them really do work. Some of them are crazier than others, but it's up to you what you think is crazy. All right. I read a book once by some guy, and, you know, he was talking about crazy ideas in science. I don't remember how many there were. Maybe it was 5, maybe it was 9. But, you know, he lined these up, and the closer you got to his field, the fewer of these ideas that were supposed to be crazy he thought were crazy. So most likely that has to do with his field, his perspective, not so much a real objective consideration about what is crazy and what's not crazy. As far as you should be concerned, all of the interpretations are crazy, and you just have to figure out a way to figure out which crazy thing is the most real. And the way you do that is with an experiment, because, again, this is physics. It's not math, right? It's not philosophy. And the real test for anything you want to do is figure out an experiment. And if you don't figure out an experiment for something, you don't understand it, okay? If you don't have an experiment, you don't understand it, all right? Anyways, thank you very much for listening, and I will talk to you later, okay? Bye now.